Basically, on my computer, OBS, Open Broadcast Software, the software I usually use to record, is broken. So I'm just using the built in screen recording feature. It is not as robust. It does not show my camera, so I apologize. But this will hopefully work better. Let me just put this up right here. So right up here, this is we're talking about the FEA project. Um, for who's grading this, um, I was sick around that time. I missed about half of that project, so this is a little out of order. But at the end of the day, I did still complete the kind of understanding the basics of it. And funnily enough, now a bit after the we did this project, Onshape has now implemented their own FEA, and so hopefully we never have to use some scale again. It wasn't that bad to deal with, but built-in FEA is a lot better than having to go to a whole nother application. So anyway, getting to the meat of it, this is so. Oh, pardon me. See, if we look at the Onshape, we are seeing this pretzel. I'll call it a pretzel. If you can't tell, there are some changes. If you can't tell, I really was sick around this time. So this is kind of my idea. My idea was, a helix. One, it looks really cool. It's funny, but also, I just learned how to do helixes from the spinner and prop assignment, which we had just done before. And so I thought, oh, this is really funny. But also, I thought maybe it has some structural integrity because there's a pattern that can hopefully kind of spread out the stress without using too much mass. And then, as you can tell, I continued to make changes, and I believe this one just had some reference changes, but this one is what I ended up changing it to. Kind of smoothing it out a little bit more because printing that, the overhangs would just not work. But let's go back to Slay 1. I know, poor naming choice. But if we go back to it, loading, we see that. And so we're going to now look at the analysis of how it works. So this is yet another version. There are a couple geometries that I made of it, a couple different versions. This is one of them, and it is different, and optimally, I would hope to have let me flip this around. I'd hope to have this version in here, but as long as you kind of understand the basic idea of why a helix like this doesn't work, I can show you. So this was a static analysis we went through, and then the simulation run. That one failed. As you can see, this is a very weird geometry. So sometimes the FEA just kind of glitches out. And we're looking at some of our, we're looking at this solution field. It's going to load. Rural internet does that to you. But yeah, so this was a really bad idea. I'll completely admit. This is not normal. That's what I'll tell you. This is not normal. That is 4,000 millimeters. That is 4 meters of displacement. If this thing did not break, it would be bending 4 meters. But it would break. This is not a realistic thing. So we're going to go to von Mises stress in millipascals. That's just ridiculous. So down here, this giant bend, there's not a lot of stress on it, right? Especially on the outer edges. And that's the problem with this design, is that despite what you may think, what I thought, there's no stress that actually gets really sent to the the outside here. It's all just put on the middle. And if you can kind of see, there's these red spots right here. So this is what's going under like 2,000 millipascals, or 2 pascals of stress, which is absolutely ridiculous. And so yeah, it's just completely ridiculous. And so we went back to the drawing board, and I ended up coming out with this. A way simpler thing. We'll leave this. Oh, pardon me. This is the wrong Park Studio. Versions are finicky. Onshape's versions implementations, I've complained about them before. They're all right. You really have to learn to use them differently than most other versioning things exist. So it's not my favorite. This is a hollow cylinder. I said, oh wow, I way over engineered the previous one, and so I'm going to under engineer this. And if we look at the, it's a hollow cylinder. That is literally it. I don't know really what to explain. I just thought, oh, you're not using a bunch of volume in the middle, but you do have this really big radius where there's no, big fins taking up mass, but it's just kind of hopefully stretching it out. Hopefully in the circle, it evenly distributes enough that it's going to be able to take a lot of pressure without, bending too far. And when it gets too much pressure, it is going to break. It's not going to bend, but it is going to break. But hopefully, it can take a lot before it does that. And then this was a random weird idea where I was still getting over the kind of over-engineering idea, where I was trying to make it skinnier as it went on to hopefully put more reinforcement at the base. I think there's merit in the idea, but it's a very complicated idea. So we're going to go back to this. This is kind of what went on the final drawing board. This is what also ended up getting printed. And if we go back to sim scale, we go to engineering for beam test part 2. Making this work basically broke the sim scale configuration so much that I basically just made a new one. As you can see, I just did another static analysis, simulation run. All this took was one run. And you could use more runs just to get kind of more data points. Granted, this is kind of the most practical theoretical can get, and also the most theoretical practical can be. Kind of weird in the middle. So this has also, so that when we get out pascals, we don't need to be in pascals anymore. This only experiences about 60 millipascals of stress, so way less. And as you see, there's still this problem where near the base you're getting a lot more stress, which makes perfect sense. So I think if I had more time, I would maybe try that tapering idea. Because as you see, a lot of this mass right here is not undergoing the most. So if you taper that off, especially in the middle right here, and you make that a little thicker, you can more evenly distribute it. And then if we're also looking at our displacement, let's go to, pardon me, that is Y, not Y displacement. We need to look at Z displacement, and we're looking at that in millimeters. We can see that this only dips down around -30. This is all well within the constraints. Frankly, I'm surprised at how the pretzel idea got to this idea and how vastly different they worked. This one worked very well. And I say my biggest reflection on that is that for some people it's really easy to over-engineer, and for some people it's really easy to just underthink something. And so if you find yourself leaning too far one way, just simplify it to what you need to, the problem you need to solve, and just take the steps from there. Do the bare minimum you think will reach, that will solve that problem. And so it, for me personally, I have a trouble with, I tend to over-engineer sometimes. And so for me, I say make it simpler. But for other people, it doesn't make it more complicated, but make it more, resilient. And for them, it's, going beyond their bare minimum, because obviously their bare minimum is likely not working. And so I think that my big thing reflection on this is not the actual process. It's not the process of designing the CAD. It's the process of how I thought about it. And even though I couldn't really physically test it too much as I was out sick, it was still a really good experiment in being able to, think about like how is this practically going to do? Because with the pretzel design, I was just shooting in the dark. Now with this, I had more of an idea and I thought more about it and I thought simpler. I didn't overthink a problem. It's not a test. The problem that's the best answer is the best answer. It's not the most complicated. It's not the hardest. It's just the best answer. So thank you, and I will see you soon.